Hi, welcome to our channel of IGNOU Audiobooks, Indira Gandhi National Open University School of Sciences, SOS. Master of Science, Biochemistry, MSCBCH. Semester 2. MBC 004 Enzymes and their Applications. Block-1 Introduction to Enzymes. Unit-2 Mechanism of Catalysis-I. 2.1 Introduction. The magnificent history of the enzyme as a molecule is entrenched in the contribution of renowned scientists and Nobel laureates that helped in the development of enzymology as a distinct entity. Two prominent scientists, Koshland and Fisher, elucidated the nature of enzyme as a molecule and tried to explain its common associated characteristic specificity and flexibility, respectively. Enzyme's activity is influenced by a number of factors such as temperature, pH, substrate concentration, etc. So that is why enzymes work best within specific temperature and pH ranges, and suboptimal conditions can be the reason an enzyme to lose its ability to bind to a substrate. Several factors affect the rate at which enzymatic reactions proceed. Activity of some enzymes gets influenced by compounds that do not seem to be directly involved in the reaction, like metal ions, detergents, and hydrophobic molecules. All enzyme assays measure either the disappearance of the substrate or appearance of product over time. Measurement of enzyme activity by different enzyme assays is vital for studying biological processes, diagnosing diseases, and designing pharmaceuticals. A large number of different methods of measuring the concentrations of substrates and products exist, and many enzymes can be assayed in different ways. Two main categories of enzyme assays: continuous and discontinuous assay, have distinct methodologies and applications. We are going to discuss more about these assays later in the unit. Expected learning outcomes. Expected learning outcomes. After studying this unit, you should be able to differentiate between Koshland and Fisher theories on enzyme-substrate interaction, factors influencing enzyme activity, distinguish between continuous and discontinuous assays, and optimization of enzyme assays. To point to Fisher lock and key hypothesis. To explain the fundamental action of single substrate enzyme, in 1894, Emil Fisher proposed that enzymes are structurally complementary to their substrates so that they fit together like a lock and key. Fig. 2.1. This model is also known as template model. According to this model, enzyme-substrate interaction is like a key fitting into its lock. Enzyme represents the lock and substrate is the key. Only the right key will be able to open the lock. Other keys that are too small or too big or are wrongly positioned will not be able to open the lock. As we have different set of keys for different locks, similarly, different enzymes poses unique active sites for variable substrates. This theory also accounts for enzyme substrate specificity. This analogy proved valuable and has vastly influenced the knowledge and development of biochemistry, since such interactions lie at the heart of many biochemical processes. Since the substrate must fit into the active site of the enzyme before catalysis can happen, only correctly devised molecules can serve as substrates for a specific enzyme. In many cases, an enzyme will react with only one naturally occurring molecule. Lock and key hypothesis is focused mainly on the active site of enzyme. Enzyme specificity is important because it helps to maintain and separate the multiple interlinked metabolic pathways involving hundreds of enzymes. However, this theory fails to explain the stabilization of enzyme. The active site of enzyme as per lock and key mechanism seems rigid, lock, and matches with the structure of substrate, key. It does not visualize the weakening of enzyme-substrate bonds proposed in transition state theory. It does not take into account the intermediate shape of the enzyme structure. Active site seems to be more static and a single entity with no separate catalytic group. The observations from X-ray diffraction studies reveal tight fitting of the substrate to a pocket, active site, in the enzyme with complementary structure, which suggests that the active site of enzyme is a much more flexible structure than postulated by lock and key model of enzyme catalysis. 2.3 Induced fit model. In view of the above-mentioned limitations of Fisher lock and key hypothesis, a second model was proposed by Koshland Jr. in 1958. He postulated that enzymes are flexible and that the shapes of the active sites can be markedly modified by the binding of substrate. In the Fisher's lock and key model, the active sites are considered to be rigid structures. But this is not the case always. It has been observed that the active sites of some enzymes assume a shape that is complementary to that of the transition state only after the substrate is bound. That is, the proximity of the substrate induces a conformational change in the enzyme molecule aligning the groups for both substrate binding and catalysis. This process of dynamic recognition is called induced fit, FIG. 2.2. The active site continuously modifies itself until and unless the substrate binds to it perfectly, which is required for further reaction. It has also been postulated that enzyme induces reciprocal changes in substrate and harness the binding energy to facilitate the transformation of substrates to products. The interactions between substrate and the enzyme and transition state formation as well as weakening of interactive bonds by nucleophilic or electrophilic attack are well explained in the induced fit mechanism. The induced fit model clarifies the characteristic features of the enzyme, specificity and flexibility. Therefore, in comparison to lock and key model, the later model gained much more acceptance. Fig. 2.2. Pictorial representation of enzyme-substrate interaction in the induced fit model. Look at the school. Generally, an enzyme-catalyzed reaction is 106 to 10-12 times faster than any non-catalyzed reaction. The enzyme-substrate interactions occur at the molecular level, so it will be difficult to find the exact and accurate nature of these processes. Even enzymes differ in their specificity. Some of the enzymes are compatible with several substrates, similar side chains or functional groups. There are several other factors that affect enzyme activity, such as temperature and pH. Let us discuss more about these factors in subsequent sections of the unit. 2.4 Factors affecting enzyme activity. You have learned that the three-dimensional structure of proteins, enzymes, is important for their catalytic activity. Apart from the peptide bond which links amino acids together in a chain, a protein is stabilized by various intermolecular forces like hydrogen bonding, van der Waals attraction, electrostatic interaction, and so on. Changes in the physical or chemical environment of an enzyme affect its structure, which in turn affects its activity. In this section you will study about various factors like temperature, pH, concentration of substrate, concentration of enzyme, concentration of product, and how these factors affect the enzyme activity. 2.4.1 Effect of temperature. Enzymes are biological catalysts. So how does change in temperature affects the enzyme activity? Every enzyme has an optimum range of temperature at which enzyme shows its maximum activity. Generally, most of the enzymes have optimal temperature of 400 C, which is close to the physiological body temperature, 37.50 C. At high temperatures, typically between 42 to 700 C, enzymes get irreversibly denatured. At temperatures above and below the optimum range, activity of enzyme declines. This is because, at very low temperature, enzyme activity gets arrested, while at very high temperatures the three-dimensional structure of the enzyme is lost. High temperature destroys the intermolecular attractions like hydrogen bonding, which lead to loss of functional structure of enzyme. Hence, the affinity of enzyme for substrate diminishes and its activity declines. Look at the temperature versus activity graph, Fig. 2.3. It's a bell-shaped curve depicting maximum enzyme activity at the optimum temperature. In this context, one important fact which you must note is that increase in rate of reaction with increase in temperature is due to increase in the number of collisions between the enzyme and substrate molecules, as well as also due to increase in the energy of these collisions. Rise in temperature is followed by increase in the velocity and kinetic energy, and with faster velocities, molecules reaching activation energy will increase, and that leads to increase in rate of reactions. Generally, 10-degree increase in temperature leads to increase in enzyme activity by 50% to 100%. The change in rate of reaction for any 100 C rise in temperature is known as its Q10 or temperature coefficient value. This value is close to 2 for most of the chemical reactions. However, for enzymatic reactions, Q10 values are lower. The increase in temperature also causes rise in the internal energy of molecules, which may include translational, vibrational, and rotational energy of molecules, the energy engaged in chemical bonding of molecules, as well as energy engaged in non-bonding interactions. However, too much heat can lead to decrease in enzyme activity due to denaturation and inactivity of either enzyme or substrate. 2.4.2 Effect of pH. Enzyme activity is influenced by pH. What is a pH value? All of you are familiar with this term right from school days. pH, i.e., negative logarithm of the reciprocal of hydrogen ion concentration. Enzymes in general work within a small range, and most of them have a particular pH at which they exhibit optimal activity. The particular pH of enzymes is the pH value at which the bonds within enzyme are influenced by the H+ and ions in such a way that the shape of the active site of enzyme is most complementary to the shape of its substrate. As you know, enzymes are proteins, and their molecular interactions are determined by the interactions among the charges displayed by amino acids present in the proteins. The interactions may involve hydrogen bonding that can be altered by changes in pH. Any change in pH most likely will alter the state of ionization of acidic or basic amino acids, e.g. amino acids USP, LYS, that plays a crucial role in the substrate binding and or the catalytic action, or else the three-dimensional structure of proteins will change. Therefore, alteration in pH leads to changes in protein function or inactivation of enzymes, leading to the loss of enzyme structure and its activity. Each enzyme, thus, acts best in a working pH range which is specific to it, and its activity slows down with any substantial change, i.e., increase or decrease in the H+ ion concentration. At optimum pH, enzymes show maximum activity. Fig. 2.4. Most of the enzymes have optimal pH of 7.4, which is also the physiological pH. The activity generally falls off on either side of this value. Deviations above 0.5 pH unit from the normal blood pH of 7.4 leads to protein denaturation. Although the covalent bonds are not broken, but even disruption of some hydrogen bonding leads to loss of enzymatic activity. Generally, optimum enzyme activities are observed at or near the isoelectric point pi of the enzymes. The pH optimum of some enzymes is given in table 2.1. For example, trypsin, whose pi value is 10.1, shows maximum activity at pH ranges between 7 and 9. Table 2.1, pH optimum of some common enzymes. SNO. Enzyme pH optimum. 1 pepsin 1.5 to 1.6. 2 lipase, stomach, 4.0 to 5.0. 3 lipase, pancreas, 8.0. 4 catalase 7.0. 5 trypsin 7.8 to 8.7. Small changes in the pH above or below the pH optimum do not lead to a lasting transformation in the enzyme, since the bonds can be renewed. However, acute changes in pH, i.e. highly acidic or highly alkaline, may eventually cause denaturation of enzymes and they will lose their function irreversibly. Enzymes in dissimilar locations may have diverse optimum pH values since their environmental settings may be different. 2.4.3 Effect of substrate concentration. The enzyme activity is measured by determining the rate of disappearance of substrate or appearance of product. Therefore, any changes in the substrate concentration will affect the rate of an enzyme catalyzed reaction. Therefore, in such condition, an increase in substrate concentration will lead to an increase in the rate of reaction. In the presence of a given amount of enzyme, at low concentration of substrate, the rate of enzyme reaction will increase with increasing substrate concentration. In this condition, the catalytic sites of enzymes are vacant and substrate can bind most of the time, so the rate of reaction is limited by the availability of substrate. The rate of reaction increases linearly until it reaches a maximum known as point of saturation, figure 2.5. The point of saturation is where maxima is attained and is denoted by Vmax. Vmax is the maximum possible rate of reaction. On reaching this stage, an increase in substrate concentration will not produce any significant change in the rate of reaction. At this stage, substrate is present in excess and all the enzyme molecules are saturated with the substrate and all the enzyme active sites are occupied by substrate molecules. The increase in substrate will not have any effect until the bound substrate molecules get released. The rate of formation of product is dependent on the enzyme activity itself. The shape of the curve depicting the effect of substrate concentration on rate of reaction enzyme activity is a hyperbola and well explained with a mathematical equation known as Michaelis-Menten equation. 2.5 Types of enzyme assays. Enzyme activity serves as a vital parameter for determining biochemical processes and catalytic reactions within biological systems. Enzyme assays are an indispensable tools used for assessing enzyme activity. Enzymatic activity assays are performed to determine the presence or amount of a selected protein in an organism, tissue, or sample. The following question may arise in the mind of learner. How does an enzyme assay work? The answer to the above question is that an enzyme assay is a laboratory technique used to measure enzyme activity. The assay involves preparation of reagents and samples and setting up of optimal reaction conditions to make the reaction feasible. Several key factors such as are temperature, pH, ionic strength and proper concentrations of the essential components like substrates and enzymes must be considered for assaying enzymes. It is always advisable to standardize the parameters, however the vast diversity of the characteristic features of different enzymes prevents unification of assay conditions. Nonetheless, several enzymes, especially those from mammalian sources, possess a pH optimum near the physiological pH of 7.5, and the body temperature of about 37 degrees Celsius can serve as assay temperature. Once the enzyme reaction is initiated and monitoring of substrate or product concentration can be done over a period of time to determine the changes. The data collected will help to determine the reaction rate. It also serves to control different parameters as well as ensure calibration accuracy. These assays provide insights into enzyme behavior and kinetics, which is very much important to assess their role in various biological pathways. Rules for assaying enzyme activity include appropriate handling, methodical aspects, preparation of assay mixtures and blanks, as well as choice of the assay time. Several other particulars of complex enzyme assays, including reversible reactions and coupled tests, also need to be considered. Enzyme assays can be divided into two groups based on their sampling method: continuous assays, where the assay gives a continuous reading of activity, and discontinuous assays, where samples are taken, the reaction stopped, and then the concentration of substrates products is determined. Let us discuss them more in detail. Continuous enzyme assay. As the name suggests, continuous assays are those assays where the assay gives a continuous reading of activity till completion. So these are often termed as endpoint assays. The enzyme activity is measured via the quantity of substrate consumed, or the amount of product formed during the reaction over a fixed period of time. Both values are directly proportional to the concentration of enzymes present in the sample. Examples of continuous assays include spectrophotometry, calorimetry, chemiluminescence, and fluorimetry. In these methods, the enzyme activity is determined by measuring the progress of reactions by light or heat. Spectrophotometric enzyme assays. In spectrophotometric assays, the course of the reaction is determined by measuring a change in the absorption of assay solution. If the absorption falls in the visible region, then the change in the color of the assay can be determined. Such assays are known as spectrophotometric assays. The MTT assay, a redox assay using a tetrazolium dye as substrate, is an example of a colorimetric assay. In several oxidation-reduction reactions, NADH or NADF are extensively used as coenzymes. These coenzymes absorb UV light in their reduced forms but not in their oxidized forms, so UV light can also be used to measure enzyme activity in oxidoreductive reactions. An oxidoreductase using NADH as a substrate could therefore be assayed by following the decrease in UV absorbance at 340 nanometers as it consumes the coenzyme. Direct versus coupled assays. There are several enzyme reactions which do not result in change in the absorption of fluorescence. In such a scenario, it is possible to measure enzyme activity indirectly using spectrophotometric or fluorometric assay for the enzyme by using a coupled assay. In coupled assay, the product of one reaction is used as the substrate of another, easily detectable reaction. For example, hexokinase catalyzes addition of phosphate group to glucose to form glucose 6-phosphate. Its enzyme activity can be measured by coupling the production of glucose 6-phosphate to NADF production using glucose 6-phosphate dehydrogenase. So coupled assays allow measurement of enzyme indirectly. Fluorometric enzyme assays. You are already familiar with fluorescence and fluorometry. When a molecule emits light of one wavelength after absorbing light of a different wavelength, it is called fluorescence. Fluorometric assays are based on the difference in the fluorescence of substrate from product to determine the enzyme activity. These assays are considered to be much more sensitive than spectrophotometric assays. However, several limitations include external and intrinsic fluorescence as well as the instability of several fluorescent compounds when exposed to light. The examples of these assays include fluorescent dyes, NADH and NADF. Since NADH and NADF are reduced forms, they are fluorescent while their oxidized forms are non-fluorescent. The increase or decrease in fluorescence in enzymatic reactions will help to determine enzyme activity. Synthetic substrates that release a fluorescent dye in an enzyme-catalyzed reaction include 4-methylambelaypyryl beta-deglucuronide for assaying beta-galactosidase. Calorimetric. In the calorimetric enzyme assays, the heat released or absorbed by chemical reactions is measured. These assays are very general, since many reactions involve some change in heat and with use of a microcalorimeter, not much enzyme or substrate is required. The calorimetric enzyme assay offers several advantages over other conventional enzyme assay techniques, such as it allows the use of natural substrates and it remain unaffected by the spectroscopic properties of the sample. Chemiluminescent enzyme assays. Chemiluminescence is the emission of light by a chemical reaction. When the excited intermediates in enzyme reactions return to their stable ground state, a photon is released, which is detected by the luminescence signal instrument to measure product formation. These types of assay can be extremely sensitive than colorimetric, fluorimetric, or radiometric assays, since the light produced can be captured by photographic film over days or weeks. Examples of such reactions include detection of horseradish peroxidase by enzymatic chemiluminescence, a very common method of detecting antibodies in Western blotting. Enzyme luciferase is another example of such reaction, which is found in fireflies and how it naturally produces light from its substrate. Luciferin. Discontinuous enzyme assays. In such enzyme assays, the reaction is stopped and then the concentration of substrate's products is determined to measure the enzyme activity. In contrast to continuous enzyme assays, discontinuous assays are performed when samples are taken at set intervals of time. Therefore, such form of enzyme assays directly or indirectly measure changes in substrate or products over time to determine the reaction rate changes. These assays involve radiometric assays as well as chromatographic assays such as HPLC or TLC. Radiometric enzyme assays. You have read about radioactivity in the course Bioanalytical Tools and Techniques. Radiometric assays measure the incorporation of radioactivity into substrates or its release from substrates. The radioactive isotopes most frequently used in these assays are 14C32P, 35S and 125I. These assays are both extremely sensitive and specific. Radioactivity is usually measured in these procedures using a scintillation counter. Chromatographic enzyme assays. As the name suggests, these chromatographic assays make use of high-performance liquid chromatography, HPLC, technique to measure product formation by separating the reaction mixture into its components. These assays are more complex and their sensitivity can be increased by labeling the substrate's products with a radioactive or fluorescent tag. A comparison of the two methods reveals that the continuous enzyme assay method is generally easy to perform, while discontinuous enzyme assays are used in scenario where higher precision or complex sample matrices are required. 2.6 Optimization of enzyme assays. Thus, the development of reproducible sensitive enzyme assays is essential for so many metabolic processes. It has wider applications in the industrial and pharma sector. The development of an in vitro enzyme assay requires consideration of multiple factors such as purity of the enzyme, pH, viscosity, anionic strength of the reaction mixture, and the addition of cofactors or other buffer additives. It is important to determine the stability of reagents under storage and assay conditions. During the optimization of an enzyme assay, the effects of the following factors are normally examined. 1. Buffer composition. 2. pH. 3. Temperature. 4. Concentration of divalent ions, e.g., Mg2+, Ca2+. 5. Concentration of ion salts, e.g., NaCl, KCl. 6. Type and concentration of reducing agents, e.g., DTT, mercaptoethanol, and 7. Solvent concentration, e.g., DMSO, polyethylene glycol, PEG. Apart from the above listed factors, the choice of detection method for following an enzymatic reaction and the size of the reaction volume are also critical. Nowadays, a lot of efforts are concentrated on miniaturization of enzymes assays to reduce the consumption of reagents and therefore the cost. However, these efforts need to skillfully determine the potential effect of miniaturization on the assay performance. 2.7 Summary. Let us summarize our unit. Times in lock and key paradigm. Emil Fischer proposed a model that depicts inflexible interactions. The shapes of enzyme and substrate are complementary, and binding induces relatively minimal conformational change. Times the induced fit model proposed by Koshland described about the conformational alterations that happen during enzyme-substrate binding. And these interactions enable several degrees of shape complementarity. In the unbound state, the model helps to explain the dynamic structure of proteins. Times on binding a ligand, an enzyme alters its conformation just as a glove changes its shape when a hand slides inside it. In the beginning, a weak initial complex is formed which is followed by intermediates that gradually reorganize to make new interactions until the final high affinity state is accomplished. Times several factors affect or alter the activity of enzymes, for example, temperature, pH and concentration of substrate, etc. Every enzyme has an optimum temperature at which it shows its maximum activity. Generally, most of the enzymes have optimal temperature of 400 C. Times generally most of the enzymes have optimal pH of 7.4, which is also the physiological pH. The activity generally falls off on either side of this value. Times enzyme activity is also affected by substrate concentration. Shape of the curve depicting the effect of substrate concentration on rate of reaction. Enzyme activity is a hyperbola and well explained with a mathematical equation known as Michaelis-Menten equation. Times enzyme assays are crucial tools used for assessing enzyme activity. These assays are established to determine the activity or concentration of enzymes. These enzymatic assays are of different types, such as based on the detection of fluorescent, luminescent, or spectrophotometric endpoint signal. Thank you.